Every atom in your body, every molecule that makes up the world around you, has a story that begins in the heart of a star. It's easy to think of starlight as just a distant twinkle in the night sky, but what if I told you that those beams of light are the very threads weaving the fabric of life itself? Today, we're diving into one of the most profound mysteries of the cosmos, how the universe transforms starlight into the building blocks of life. This isn't just a story about stars, it's the story of you, me, and everything that exists. From the fiery hearts of ancient suns to the delicate dance of molecules that sparked life on Earth, we'll explore the breathtaking process of celestial alchemy. By the end of this journey, you'll see the night sky not just as a beautiful backdrop, but as the cosmic workshop where the elements of life are forged. Ready to uncover how the universe turned starlight into you? Let's begin. Deep within the heart of every star lies a cosmic forge, a place where the simplest elements are transformed into the building blocks of the universe. It all begins with hydrogen, the most abundant element in the cosmos. Under immense pressure and heat, stars ignite nuclear fusion, a process that combines hydrogen atoms to form helium. But this is just the first step in a grand stellar alchemy. As stars age, they begin to fuse helium into heavier elements like carbon, oxygen, and even iron. Each fusion reaction releases energy, keeping the star shining brightly for millions or even billions of years. The life cycle of a star is a delicate balance between the crushing force of gravity and the outward pressure generated by fusion. Gravity pulls matter inward, compressing the star's core and raising its temperature. This heat triggers fusion, creating energy that pushes back against gravity's pull. For most of a star's life, these forces are in equilibrium, allowing it to burn steadily. But when a star exhausts its fuel, gravity gains the upper hand, leading to dramatic transformations. Smaller stars, like our Sun, expand into red giants before shedding their outer layers, leaving behind a glowing core called a white dwarf. Larger stars, however, meet a far more explosive fate. When a massive star runs out of fuel, its core collapses under gravity's immense force, triggering a supernova, one of the most energetic events in the universe. In a matter of seconds, a supernova can outshine an entire galaxy, releasing enough energy to fuse elements heavier than iron, like gold, silver, and uranium. These elements are then scattered into space, enriching the surrounding gas clouds with the ingredients for new stars, planets, and even life. Every atom in your body, from the calcium in your bones to the iron in your blood, was forged in the hearts of ancient stars and scattered across the cosmos by these colossal explosions. The diversity of elements produced by stars is staggering. Smaller stars primarily create lighter elements, while massive stars and supernova generate the heavier ones. This intricate dance of creation and destruction ensures that the universe is filled with the raw materials needed for planets, moons, and life itself. Without the life and death of stars, the periodic table would be far emptier, and the universe as we know it would not exist. So, the next time you gaze at the night sky, remember that you're not just looking at distant points of light. You're witnessing the cosmic factories that shape the very essence of existence. Deep within the cosmos, hidden among the swirling arms of galaxies, lie the cradles of creation's stellar nurseries. These are not the serene, glowing landscapes we often picture, but chaotic, turbulent regions where the raw ingredients of the universe come together under the relentless pull of gravity. Imagine a vast, dark cloud stretching across light years, filled with hydrogen gas and fine cosmic dust. This is a molecular cloud, the birthplace of stars. Within these clouds, pockets of gas and dust begin to clump together, drawn by their own gravity. As these clumps grow denser, they heat up, and the pressure at their cores intensifies. This is the first spark of a star's life, a delicate balance between gravity's pull and the outward push of heat and pressure. But it's not just gravity at work here. Turbulence within the cloud, often triggered by nearby supernova explosions or the collision of galaxies, stirs the cosmic pot, creating the perfect storm for star formation. Molecular clouds are more than just passive nurseries, they're dynamic, ever-changing environments. Magnetic fields thread through these clouds, shaping how matter moves and collapses. Radiation from nearby stars can erode parts of the cloud, while shockwaves from stellar winds compress other regions, triggering new rounds of star birth. It's a cosmic dance of forces, each playing its part in the grand process of creation, and when a star finally ignites, it doesn't just light up the darkness, it begins a transformation that will ripple across the universe. The elements forged in its core will one day become the building blocks of planets, moons, and even life itself. Stellar nurseries are where it all begins, the starting point for the alchemical magic that turns starlight into the very fabric of existence. Stars, those brilliant beacons in the night sky, are far more than just points of light. They are cosmic forges, shaping the very elements that make up our universe. But like all things, stars are born, they live, and eventually they die. This journey, known as a star's life cycle, is a story of incredible transformation, driven by forces that stretch the imagination. Let's take a closer look at how a star's life unfolds, from its humble beginnings to its dramatic end. It all starts in vast clouds of gas and dust scattered across galaxies. These clouds, called nebulae, are the nurseries where stars are born. When gravity begins to pull these particles together, they form a dense, spinning core known as a protostar. Over time, the pressure and temperature at the core rise until nuclear fusion ignites, marking the birth of a star. This is the moment it joins the main sequence, the longest and most stable phase of its life. Here, stars like our Sun spend billions of years converting hydrogen into helium, releasing the energy that lights up the cosmos. But not all stars are the same. A star's mass plays a crucial role in shaping its destiny. Smaller stars, like red dwarfs, burn slowly and steadily, living for trillions of years. Meanwhile, massive stars burn through their fuel at an astonishing rate, shining brightly but living fast and dying young. As a star ages, it begins to change. When it exhausts the hydrogen in its core, it swells into a red giant or supergiant, depending on its size. This phase is marked by dramatic expansion, where the star's outer layers cool and glow with a reddish hue. For stars like our Sun, the journey ends relatively quietly. After shedding its outer layers, the core collapses into a dense remnant called a white dwarf, surrounded by a glowing shell of gas known as a planetary nebula. But for the most massive stars, the end is far more spectacular. When their cores can no longer support their own weight, they collapse under gravity and explode in a supernova, a cataclysmic event that outshines entire galaxies. These explosions are so powerful that they forge elements heavier than iron, scattering them into space. And here's the remarkable part: every element in the universe, from the carbon in your body to the gold in your jewelry, was created in the hearts of stars or in the fiery aftermath of their deaths. Stars are the ultimate alchemists, transforming simple elements into the building blocks of planets, life, and even us. By understanding their life cycles, we gain a deeper appreciation for the intricate processes that shape the cosmos and our place within it. When a massive star reaches the end of its life, it doesn't fade quietly into the cosmic background. Instead, it goes out with a bang, a supernova, one of the most energetic events in the universe. These explosions are not just awe-inspiring displays of cosmic power. They are also the ultimate factories for the elements that make up everything around us. Inside the heart of a massive star, immense pressure and heat fuse lighter elements like hydrogen and helium into heavier ones, such as carbon, oxygen, and even iron. But it's only during the supernova explosion that the most exotic elements like gold, silver, and uranium are created. This violent process scatters these newly forged elements into space, enriching the cosmos with the building blocks of planets, life, and even you and me. The conditions required for a supernova are extreme. When a star several times more massive than our Sun exhausts its nuclear fuel, its core collapses under its own gravity. This collapse happens in a fraction of a second, releasing an enormous amount of energy. The outer layers of the star are then blasted outward in a shockwave that outshines entire galaxies for a brief moment. This explosion is so powerful that it can outshine all the stars in its host galaxy combined. But the story doesn't end there. The remnants of these supernovae, filled with newly created elements, expand into space, forming vast, colorful clouds of gas and dust. These remnants are not just cosmic debris, they are the seeds for future generations of stars and planets. Over millions of years, gravity pulls these materials together, forming new stellar nurseries where the cycle begins anew. Supernova are more than just destructive events. They are essential to the cosmic cycle of creation and renewal. Without them, the universe would lack the diversity of elements needed for complex chemistry, planetary systems, and life itself. Every atom of oxygen you breathe, every molecule of carbon in your body, and every speck of gold in your jewelry was once forged in the heart of a dying star and scattered across the cosmos by a supernova. These celestial explosions remind us that even in destruction, there is creation, a universal dance that shapes the very fabric of existence. When we think of the universe's heaviest elements, gold and platinum often come to mind, precious metals that have captivated humanity for centuries. But where do these elements come from? While supernovae are often credited with forging many of the elements we know, there's another cosmic powerhouse at work: neutron stars. These incredibly dense remnants, born from the collapse of massive stars, pack the mass of a sun into a city-sized sphere. And when two neutron stars collide, the result is nothing short of spectacular: a kilonova, an event so energetic it can outshine entire galaxies for a brief moment. During these collisions, the extreme conditions create a cosmic alchemy unlike anything else. The immense gravitational forces and temperatures unleash a torrent of neutrons, which bombard atomic nuclei, rapidly building heavier and heavier elements. This process, known as the Rapid Neutron Capture Process, or R process, is responsible for producing some of the universe's most exotic and valuable elements, like gold, platinum, and uranium. It's a reminder that even in the most violent events, beauty and value can emerge. But neutron stars don't just create these elements, they also play a key role in distributing them across the cosmos. When a kilonova occurs, it sends shockwaves through space, scattering these newly formed heavy elements into the surrounding interstellar medium. Over billions of years, these materials become part of new stars, planets, and even life itself. In a very real sense, the jewelry you wear or the electronics you use might contain atoms forged in the heart of a neutron star collision. This cosmic recycling process highlights how interconnected everything in the universe truly is. From the remnants of ancient stars to the elements that make up our world, neutron stars are a vital link in the chain of creation. They remind us that even the rarest and most precious things have their origins in the most extraordinary events. And as we continue to study these celestial phenomena, we uncover not just the secrets of the cosmos, but also our own place within it. When a star reaches the end of its life, it doesn't just vanish, it leaves behind a legacy, scattering its essence across the cosmos. This cosmic dust, fine particles of elements like carbon, silicon, and iron, becomes the foundation for something extraordinary. Picture tiny grains, no larger than a fraction of a millimeter, drifting through the vast emptiness of space. These seemingly insignificant specks are anything but ordinary. They are the seeds of worlds, the building blocks of planets, and the carriers of the very ingredients that make life possible. So, what exactly is cosmic dust made of? It's a mix of heavy elements forged in the hearts of stars, from oxygen and nitrogen to more complex molecules like silicates and carbon compounds. These grains are far more than just debris. They are the remnants of stellar explosions and the remnants of ancient stars that once illuminated the universe. Over time, gravity pulls these particles together, clumping them into larger and larger structures. This process, slow yet relentless, is how planets begin to take shape. But how does cosmic dust go from floating particles to something as massive as a planet? It all starts with collision and cohesion. As dust grains drift through space, they bump into one another, sticking together due to electrostatic forces. Over millions of years, these tiny clumps grow into pebbles, then boulders, and eventually into planetesimals, the building blocks of planets. These planetesimals continue to collide and merge, their gravity increasing as they grow, until they form the rocky cores of planets like Earth or the icy bodies in the outer reaches of a solar system. What's truly fascinating is that cosmic dust doesn't just create planets, it carries the potential for life itself. Within these grains, scientists have found organic molecules, the precursors to amino acids and other compounds essential for life. It's as if the universe is scattering the ingredients for its own recipe, ensuring that wherever conditions are right, the possibility of life exists. This dust, born from the death of stars, becomes the canvas on which new worlds, and perhaps new life, are painted. The story of cosmic dust is a reminder of how interconnected the universe truly is. From the ashes of dying stars to the birth of planets, it's a cycle that has repeated countless times across billions of years. And as we look up at the night sky, we're not just gazing at distant stars, we're witnessing the ongoing process of creation, one speck of dust at a time. Light is far more than just the glow we see in the night sky. It's a cosmic architect, shaping the very building blocks of existence. At its core, light is energy, carried by photons, and these tiny particles are the unsung heroes in the alchemy of the universe. When stars burn, they don't just emit light, they unleash a torrent of photons that interact with the matter around them, sparking reactions that transform simple elements into the complex molecules that make up everything we know. Take hydrogen, for example, the most abundant element in the cosmos. Under the intense heat and pressure within stars, hydrogen atoms fuse to form helium, releasing energy in the form of light. But the story doesn't end there. That light, those photons, escape the star and travel through space, carrying the energy needed to drive further chemical reactions. When they encounter dust clouds or gas, they can ionize atoms, stripping away electrons and creating charged particles that are more likely to bond and form new compounds. It's a delicate dance of energy and matter, where light acts as both a catalyst and a messenger. And it's not just about what happens inside stars. Light from distant stars and galaxies travels across the universe, bringing with it information about the chemical makeup of those far-off regions. By analyzing the light that reaches us, what we call spectroscopy, scientists can determine the elements present in a star or a gas cloud billions of light years away. Each element absorbs and emits light at specific wavelengths, creating a unique fingerprint. Through this cosmic detective work, we've discovered everything from the iron in distant supernova to the oxygen in ancient galaxies. But light's role goes even deeper. It's not just about revealing what's out there, it's about shaping the universe itself. In the early days of star formation, light from the first stars ionized the surrounding hydrogen, creating the conditions for galaxies to form. Without light, the universe would be a very different place, dark, cold, and lifeless. It's through this interplay of light and matter that the cosmos evolves, creating the diversity of elements and molecules that make life possible. So the next time you look up at the stars, remember, you're not just seeing points of light, you're witnessing the ongoing process of cosmic creation, where light is the silent force behind the chemistry of the universe. It's a reminder that even the smallest particles of energy can have an extraordinary impact, shaping the story of existence itself. Out in the vast emptiness of space, where temperatures plummet to hundreds of degrees below freezing and darkness stretches endlessly, something extraordinary happens. The atoms forged in the hearts of stars don't just float aimlessly, they collide, connect, and create the very foundations of life itself. This is where the chemistry of the cosmos begins, a process so delicate yet so powerful that it turns the simplest elements into the building blocks of existence. Take hydrogen, for example. It's the most abundant element in the universe, born from the Big Bang itself. In the cold, sparse environment of interstellar space, hydrogen atoms meet and bond, forming molecules of hydrogen gas. These clouds of hydrogen, drifting through the cosmos, become the nurseries for future stars and planets. But that's just the start. Water, one of the most essential molecules for life as we know it, also forms in these frigid, seemingly inhospitable regions. Oxygen atoms, created in the fiery cores of stars, mingle with hydrogen, and under the right conditions, they form water molecules. Even in the vacuum of space, where conditions are far from ideal, the chemistry of life finds a way. And then there are the more complex organic molecules, carbon-based compounds that are the precursors to life. In the cold molecular clouds of space, carbon atoms bond with hydrogen, oxygen, and nitrogen, creating molecules like methanol, formaldehyde, and even amino acids. These aren't just random chemicals, they're the ingredients for planets, for oceans, and ultimately, for life itself. What's truly remarkable is how these molecules form in an environment that seems so hostile. Space is cold, dark, and filled with radiation, yet it's also a place of incredible chemical activity. The collisions between atoms, though rare, are driven by the laws of physics and chemistry, creating a cosmic dance that has been going on for billions of years. This process isn't just a scientific curiosity, it's a reminder of how interconnected the universe is. The atoms in your body, the water you drink, and the air you breathe all trace their origins back to these molecular clouds in space. They are the threads that weave together the story of the cosmos, from the simplest atoms to the most complex molecules, and ultimately, to life itself. Interstellar clouds are more than just vast, swirling collections of gas and dust. They're cosmic cauldrons where the ingredients for life itself begin to take shape. Imagine these clouds as sprawling chemical laboratories, far more intricate than any we could build on Earth. Within their cold, dark depths, temperatures hover just a few degrees above absolute zero, creating an environment where atoms and molecules move slowly enough to bond in ways that wouldn't be possible under warmer, more chaotic conditions. But why does this matter? It's in these frigid, seemingly lifeless clouds that complex molecules, including amino acids, the building blocks of proteins, begin to form. These molecules aren't just random byproducts, they're the precursors to life as we know it. The process starts with simple gases like hydrogen and carbon monoxide, which collide and react under the influence of cosmic radiation. Over time, these reactions grow increasingly complex, eventually producing organic compounds that could one day become part of living organisms. One key factor in this process is the role of radiation. While it might seem counterintuitive, the faint glow of starlight and the occasional burst of cosmic rays actually help drive these chemical reactions. Radiation provides the energy needed to break apart existing molecules, freeing atoms to form new and more intricate structures. At the same time, the low pressure within these clouds allows these newly formed molecules to linger, giving them time to grow and interact without being torn apart by external forces. It's a delicate balance: too much radiation and the molecules disintegrate, too little and the reactions stall. But in these interstellar clouds, nature has found the perfect recipe for complexity. And it's not just amino acids that form here. Scientists have detected sugars, alcohols, and even compounds related to DNA floating within these cosmic clouds. Each discovery brings us closer to understanding how the universe transforms starlight into the building blocks of life. What's truly astonishing is how these molecules, forged in the depths of space, can eventually find their way to planets like Earth. Through processes like comet impacts and the gravitational pull of forming stars, these organic compounds are delivered to worlds where they can spark the beginnings of life. So the next time you look up at the night sky, remember, those distant clouds aren't just making stars, they're crafting the very ingredients that make life possible. Radiation is one of the most fascinating forces in the cosmos, shaping the very building blocks of life in ways that might seem contradictory at first. On one hand, it has the power to tear molecules apart, stripping them down to their atomic components. On the other, it can act as a cosmic catalyst, driving the formation of new and complex molecules. This delicate dance of destruction and creation is happening all around us, fueled by the energy streaming from stars, supernova, and other cosmic phenomena. Take ultraviolet light, for example. While it might be best known for giving us sunburns here on Earth, in the vastness of space, it plays a critical role in molecular chemistry. When ultraviolet light interacts with gas clouds in interstellar space, it can break apart simple molecules like water or carbon monoxide. But here's the twist: that same radiation can also energize atoms and molecules, pushing them to collide and bond in ways that create more complex structures. It's a bit like a cosmic demolition crew that also happens to be a master builder, tearing down the old to make room for the new. Cosmic rays, another form of radiation, add another layer to this process. These high-energy particles, often traveling at nearly the speed of light, can penetrate deep into molecular clouds. When they collide with atoms or molecules, they can trigger a cascade of reactions, producing entirely new compounds. Think of it as a cosmic chemistry lab, where the energy from these collisions sparks the formation of molecules that might otherwise never exist. And it's not just about individual molecules. Radiation shapes the chemistry of entire regions of space. In dense molecular clouds, where stars are born, radiation helps create the conditions necessary for complex organic molecules to form. These molecules, some of which are precursors to life, are scattered throughout the universe, waiting to be incorporated into new stars, planets, and perhaps even living organisms. So, while radiation might seem destructive, it's also a key player in the grand alchemy of the cosmos. Without it, the universe would lack the rich chemical diversity that makes life possible. It's a reminder that even in the harshest environments, there's a delicate balance at work, one that transforms starlight into the building blocks of everything we know. Around a young star, a swirling disk of gas and dust begins to take shape, a cosmic nursery where the building blocks of planets are born. These protostellar disks, as they are called, are more than just leftovers from star formation. They're the cradles of entire planetary systems. Within these disks, tiny grains of dust collide, stick together, and slowly grow into pebbles, then boulders, and eventually the seeds of planets. But how does this chaotic mess of material transform into the orderly worlds we see today? It all starts with gravity, the invisible hand that pulls everything together. Over millions of years, clumps of material grow larger, their gravitational pull attracting even more gas and dust, until they become protoplanets, the early versions of the planets we know. In the inner regions of the disk, closer to the star, temperatures are higher, causing volatile elements like water and methane to evaporate. What remains are heavier materials like metals and silicates, which clump together to form rocky planets like Earth and Mars. Farther out, where it's cooler, gas giants like Jupiter and Saturn take shape, their massive atmospheres capturing the abundant hydrogen and helium that couldn't survive closer to the heat. And in the icy outer reaches, beyond the gas giants, smaller bodies like comets and dwarf planets begin to coalesce, preserving the pristine materials of the early solar system. But it's not just about the planets themselves. These disks also give birth to moons, asteroids, and rings, creating the rich diversity of objects we see orbiting stars. What's even more fascinating is that these disks aren't static. They're dynamic, chaotic environments where collisions, migrations, and even the star's own radiation can shape the final architecture of a planetary system. Some planets might form close to their star, only to be flung outward into the cold depths of space. Others might spiral inward, consumed by the star itself. And in the right conditions, a planet might end up in the habitable zone, where liquid water and potentially life could exist. Protostellar disks are more than just a stage for planet formation. They're the architects of possibility, crafting the conditions that could one day give rise to worlds teeming with life. The story of how planets form is nothing short of cosmic alchemy, where the tiniest grains of dust transform into the worlds we see today. It all begins within the swirling chaos of a protostellar disk, a vast, rotating cloud of gas and dust surrounding a young star. Here, particles collide and stick together, forming clumps that grow larger over time. This process, known as accretion, is the first step in building a planet. But it's not just a matter of dust sticking together. The environment plays a crucial role. The temperature and density of the disk determine which materials can survive and where they accumulate, setting the stage for the diversity of planets we observe in the universe. As these clumps grow, they begin to exert their own gravity, pulling in more material and accelerating their growth. Imagine a snowball rolling downhill, gathering more snow with each turn, except this snowball is made of rock, metal, and ice, hurtling through space. Over millions of years, these planetesimals, as they are called, grow massive enough to shape themselves into spheres under their own gravity, but the journey doesn't end there. Inside these young worlds, intense heat from radioactive decay and collisions causes the materials to melt and separate, a process known as differentiation. Denser elements like iron sink to the core, while lighter materials rise to form the crust and mantle. This layering gives planets their internal structure, from Earth's molten core to the icy crusts of distant moons. The composition of a planet is deeply tied to its birthplace within the protostellar disk. Close to the star, where temperatures are high, only metals and silicates can survive, leading to the formation of rocky planets like Earth and Mars. Farther out in the cooler regions, ices and gases dominate, giving rise to gas giants like Jupiter and Saturn, or icy worlds like Neptune. This intricate dance of chemistry and physics shapes not only the size and type of a planet, but also its potential to support life. And as we explore these processes, we uncover the origins of our own solar system and the countless others scattered across the cosmos. Water is often called the universal solvent, and for good reason. It's the foundation of life as we know it. But where does this vital molecule come from in the first place? Surprisingly, water forms in the cold, dark voids of space, far from the warmth of stars. When hydrogen and oxygen atoms meet in the frigid reaches of interstellar clouds, they bond to create water molecules, which then cling to tiny grains of dust. Over time, these icy grains become the building blocks of planets and comets. But how does this cosmic water make its way to planets like Earth? Comets and asteroids play a crucial role in delivering water to young worlds. These icy travelers, often referred to as cosmic snowballs, carry water across vast distances. When they collide with planets, they release their precious cargo, seeding the surface with water. On Earth, this process may have filled our oceans billions of years ago, setting the stage for life to emerge. But water doesn't just sit passively on a planet's surface, it actively shapes its environment. Rivers carve landscapes, oceans regulate climates, and even underground water can alter the geology of a world. The search for water beyond Earth has become one of the most exciting frontiers in space exploration. From the icy moons of Jupiter and Saturn, like Europa and Enceladus, to the frosty poles of Mars, scientists are uncovering clues that water might exist in places we once thought barren. Each discovery raises the tantalizing possibility that life could thrive in these alien environments. After all, where there's water, there's potential for life, or at least the conditions that could support it. Understanding water's role in planetary evolution isn't just about unraveling the past, it's about glimpsing the future. By studying how water shapes worlds, we gain insights into where life might exist elsewhere in the universe. And as we continue to explore, one question remains: could the next great discovery of water, and perhaps life, be just around the corner, out in the vast expanse of space, where temperatures plunge to extremes and radiation fills the void? Something extraordinary is happening. Organic molecules, the very ingredients that make life possible, are forming and spreading across the cosmos. These compounds, from simple amino acids to complex sugars, are scattered throughout the universe, hidden in the icy clouds of interstellar space and embedded within ancient meteorites. But how do these molecules, so essential to life, come to exist in such inhospitable environments? The story begins in the cold, dark clouds of gas and dust that drift between stars. Within these cosmic nurseries, simple atoms like carbon, hydrogen, and oxygen collide and bond, forming more complex molecules. Over time, Cosmic rays and ultraviolet radiation provide the energy needed to spark chemical reactions, transforming these basic elements into the organic compounds we recognize as the precursors to life. It's a process that's both delicate and relentless, shaped by the harsh conditions of space, yet capable of producing the very building blocks that sustain us. One of the most remarkable discoveries came from meteorites, ancient fragments of asteroids that have fallen to Earth. Scientists have found amino acids, the molecules that form proteins, preserved within these space rocks. These aren't just any amino acids, they're the same ones that make up the proteins in our own bodies. This suggests that the ingredients for life aren't unique to Earth, they're woven into the fabric of the universe itself. But it doesn't stop there. Interstellar clouds, those vast regions of gas and dust, are also teeming with organic molecules. Telescopes have detected sugars like glycolaldehyde, which plays a role in forming RNA, a molecule essential for life as we know it. These findings paint a picture of a universe that's not only capable of creating life's building blocks, but perhaps even predisposed to do so. What does this mean for the origins of life? It suggests that the raw materials for life are abundant and widespread, scattered across the cosmos long before planets like Earth even formed. The universe, it seems, has been preparing the stage for life for billions of years. And as we continue to explore, we're uncovering more clues about how these molecules might have traveled through space, eventually finding their way to planets where life could take root. So, the next time you look up at the night sky, remember this: the stars above aren't just distant points of light. They're part of a vast, interconnected system that's been crafting the very essence of life for eons. And within that cosmic dance, the story of how starlight transforms into the building blocks of life continues to unfold. In the vast expanse of space, comets and asteroids are more than just ancient rocks hurtling through the void. They're cosmic couriers, delivering the essential ingredients for life itself. Picture these celestial travelers as nature's own supply ships, packed with water, organic molecules, and other building blocks necessary for the emergence of life. But how do these objects come to be, and what exactly are they made of? Comets, often called dirty snowballs, are icy remnants from the early solar system, composed of frozen gases, dust, and rocky material. Asteroids, on the other hand, are primarily rocky or metallic bodies, leftovers from the formation of planets. Both types of objects formed billions of years ago in the chaotic aftermath of the solar system's birth. Their compositions tell a story of the raw materials that once swirled around our young sun, waiting to be shaped into something more. When comets and asteroids collide with planets, they don't just leave craters, they leave behind the very ingredients that make life possible. For example, comets are rich in water ice, and when they strike a planet, that ice can melt, releasing water into the environment. Asteroids, meanwhile, often carry carbon-based compounds and metals, which can kickstart chemical reactions essential for life. But their role doesn't end there. These collisions also play a critical part in planetary evolution. When a comet or asteroid strikes a planet, the energy released can reshape the surface, create new environments, and even influence the planet's climate. Over billions of years, these impacts have helped shape the worlds we see today, turning barren landscapes into places where life could one day thrive. So, the next time you gaze up at the night sky, remember, those distant comets and asteroids aren't just wandering space rocks. They're the messengers of life, carrying the very elements that make our existence possible. Without them, the story of life on Earth, and perhaps elsewhere in the universe, might never have begun. the discovery of exoplanets has transformed our understanding of the universe, revealing a cosmic tapestry filled with worlds beyond our solar system. Among the thousands of planets identified, one question burns brighter than the rest. Could any of these distant worlds support life? To answer this, astronomers focus on what's known as the habitable zone, a region around a star where conditions might allow liquid water to exist on a planet's surface. Water, as we know it, is essential for life as we understand it, making this zone a critical starting point in the search for habitable worlds. But finding a planet in the habitable zone is just the beginning. Starlight plays a pivotal role in shaping a planet's environment. The type of star a planet orbits, its brightness, and even its stability all influence whether a world could sustain life. For example, smaller, cooler stars like red dwarfs emit less heat, meaning their habitable zones are much closer to the star. However, planets orbiting too close risk being bombarded by intense stellar flares, which could strip away their atmospheres. On the other hand, larger, hotter stars might offer more stable environments, but their shorter lifespans could cut short the window for life to emerge. Detecting life on these distant worlds is another monumental challenge. Even with advanced telescopes, we're limited to indirect methods. Scientists look for biosignatures, chemical clues in a planet's atmosphere that could hint at biological activity. Oxygen, for instance, is a strong indicator, but it's not definitive on its own. Other gases like methane, combined with oxygen, could suggest a more compelling case for life. Yet, interpreting these signals requires precision, as natural processes can sometimes mimic the same chemical signatures. The search for habitable exoplanets is a race against time and technology. Every discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? And while the challenges are immense, the possibility of finding a world teeming with life keeps astronomers, and all of us looking to the stars with hope and wonder. Starlight is far more than a cosmic spotlight, it's a sculptor of worlds. When we look at planets orbiting stars, we often think of light as just a source of illumination, but its role goes much deeper. The radiation streaming from a star, particularly ultraviolet light, plays a critical part in shaping the very air or lack of it around a planet. It's this starlight that drives the complex chemistry of planetary atmospheres, influencing everything from temperature to the potential for life. Imagine a young star pouring energy into its neighboring planets. The ultraviolet rays from that star don't just warm the surface, they break apart molecules in the atmosphere, triggering chemical reactions that can create entirely new compounds. For example, on Earth, ultraviolet light from the sun splits oxygen molecules, which then recombine to form ozone. This ozone layer acts as a shield, protecting life from harmful radiation. But on other planets, depending on their distance from their star and the composition of their atmospheres, this process can lead to wildly different outcomes. Some may develop thick, protective layers, while others might see their atmospheres stripped away entirely. Stellar winds also play a crucial role in this cosmic dance. These streams of charged particles, ejected from stars, can erode a planet's atmosphere over time. Take Mars, for instance. Scientists believe that billions of years ago, it had a much thicker atmosphere, but the relentless bombardment of solar winds gradually stripped it away, leaving the thin, cold air we see today. On the flip side, some planets with strong magnetic fields can deflect these winds, preserving their atmospheres and potentially creating stable environments where life could thrive. The interplay between starlight and planetary atmospheres doesn't stop there. The type of star matters too. Smaller, cooler stars, like red dwarfs, emit less ultraviolet light, but are prone to violent flares that can bombard nearby planets with intense radiation. This could make it challenging for atmospheres to develop or remain stable. In contrast, planets orbiting larger, hotter stars might face a different set of challenges, such as extreme heat and rapid atmospheric loss. Each scenario paints a unique picture of how starlight shapes the potential for habitability. As we explore distant worlds, understanding this relationship between stars and atmospheres becomes key to identifying planets that could support life. It's not just about finding water or the right temperature. It's about the delicate balance of light, radiation, and chemistry that makes a planet truly livable. And as we uncover more about these processes, we're reminded of just how interconnected everything in the cosmos truly is. The idea of the Goldilocks Zone feels almost magical, like a cosmic sweet spot where life might find its footing. It's not too hot, not too cold, but just right. This region around a star, often called the habitable zone, is where planets can maintain liquid water on their surfaces, a key ingredient for life as we know it. But how did this concept come to be, and how do we define its boundaries? The story begins with our own solar system. Earth sits comfortably in this zone, while Venus and Mars lie just outside it, one scorching and the other frozen. This observation sparked the idea that life might thrive only under very specific conditions. Over time, our understanding of the habitable zone has grown more nuanced. It's not just about distance from a star. Factors like a planet's atmosphere, its composition, and even its ability to retain heat play a role. For example, a thick atmosphere could trap enough warmth to make a distant planet habitable, while a thin one might leave a closer planet barren. Even a planet's tilt and rotation can affect its climate, adding layers of complexity to the search for life-friendly worlds. But the Goldilocks Zone isn't the whole story. Scientists are discovering that life might not always follow the rules we've set. Take Europa, one of Jupiter's moons. It's far from the sun's warmth, yet beneath its icy crust lies a vast ocean that could harbor life. Or consider Enceladus, a tiny moon of Saturn, where geysers of water spew into space, hinting at a hidden ocean below. These discoveries challenge our assumptions and remind us that the universe is full of surprises. The search for planets in the habitable zone has also revealed incredible diversity. From rocky super-Earths to water worlds shrouded in thick atmospheres, each discovery expands our understanding of where life might exist. But here's the catch: the Goldilocks Zone is a starting point, not a guarantee. A planet might have the right conditions but lack the chemistry needed for life. Or it might have all the ingredients but face other challenges, like intense radiation or a volatile climate. So while the habitable zone is a powerful tool in our search for life, it's not the final word. The universe is vast and full of possibilities, and life might find a way in the most unexpected places. As we continue to explore, one thing is certain: the story of where life can thrive is far from over. Life has a remarkable way of adapting, even in places where it seems impossible to survive. Take extremophiles, for example, organisms that thrive in environments most of us would consider utterly hostile. These tiny pioneers of resilience have been found in the crushing depths of ocean trenches, near scorching hydrothermal vents, and even in the acidic waters of hot springs. Their existence challenges our understanding of what it means to be alive and expands the boundaries of where life might exist. What makes extremophiles so fascinating isn't just their ability to endure extreme conditions, but how they do it. Some, like thermophiles, flourish in blistering heat by evolving proteins that remain stable at temperatures that would destroy most other life forms. Others, like acidophiles, thrive in highly acidic environments by developing unique cellular structures that protect them from corrosive surroundings. These adaptations aren't just quirks of nature, they're profound clues about the versatility of life itself. But why does this matter beyond Earth? The discovery of extremophiles has reshaped how we think about the search for extraterrestrial life. If organisms can survive in the freezing vacuum of space or the boiling cauldrons of Yellowstone's hot springs, then maybe life isn't confined to Earth-like conditions. Planets and moons once deemed uninhabitable like Mars with its harsh surface or Europa with its icy oceans suddenly seem like potential hotspots for life. Extremophiles remind us that life is far more adaptable than we once thought, and the universe might be teeming with organisms in places we've yet to imagine. This isn't just speculation, it's science in action. Missions to Mars and Europa are designed with extremophiles in mind, searching for signs of life in environments that mimic Earth's most extreme habitats. Every discovery here on Earth sends ripples through the cosmos, reshaping our expectations and fueling our curiosity. Who knows, the next breakthrough in our search for extraterrestrial life might come from studying a tiny organism thriving in a place we once thought barren. Magnetic fields are like invisible shields, wrapping planets in a protective embrace. But how do they form? It all starts deep within a planet's core. For Earth, the swirling molten iron in its outer core generates electric currents, which in turn create a powerful magnetic field. This process, known as the dynamo effect, acts like a cosmic generator, producing a barrier that extends far into space. Without this magnetic shield, our atmosphere would be stripped away by the relentless bombardment of solar winds and cosmic radiation, leaving the surface exposed to harmful particles. But magnetic fields do more than just deflect radiation, they also help preserve a planet's atmosphere. Think of it as a cosmic umbrella. Earth's magnetic field deflects charged particles from the sun, preventing them from eroding our atmosphere over time. This protective layer is essential for maintaining the delicate balance of gases that make life possible. Without it, the atmosphere would slowly bleed away, turning a vibrant, habitable world into a barren wasteland. Detecting magnetic fields on distant exoplanets, however, is no easy task. Unlike atmospheres or surface features, magnetic fields are invisible and don't emit light. Scientists rely on indirect methods, such as observing how a planet interacts with its host star's radiation, or analyzing the presence of auroras in its atmosphere. These clues can hint at the existence of a magnetic field, but confirming its presence remains one of the biggest challenges in exoplanet research. Yet, understanding these fields is critical. Without them, even planets in the so-called habitable zone might not be able to support life as we know it. The interplay between magnetic fields and habitability opens up fascinating questions. Could a planet with a weak magnetic field still sustain life? What if a planet's magnetic field fluctuates over time, like Mars did in its distant past? These are the kinds of mysteries that keep astronomers and astrobiologists searching the cosmos, piecing together the intricate puzzle of what makes a world truly livable. When we look up at the night sky, one question lingers in our minds: are we alone? To answer this, scientists have turned their gaze to the stars, searching for biosignatures, hints of life that can be detected even from vast distances. But what exactly makes up a biosignature? These are not just any signs. they're clues left behind by living organisms, whether in the form of gases in a planet's atmosphere or unique patterns on its surface. Think of it like finding footprints in the sand, except these footprints might be hidden in the chemical makeup of distant worlds. One of the most promising biosignatures is the presence of certain gases in a planet's atmosphere. For example, oxygen is often seen as a strong indicator of life, since it's a byproduct of photosynthesis. But here's the twist: oxygen can also be produced by non-biological processes, like water molecules splitting in the atmosphere of a planet bombarded by ultraviolet light. This is where the challenge lies, distinguishing between what's created by life and what's simply a quirk of planetary chemistry. Scientists must look for combinations of gases, like oxygen alongside methane, which would be harder to explain without the presence of living organisms. Surface features also play a role in the search for life. Imagine a world covered in vast, green forests or oceans teeming with microbial mats. These could leave behind detectable patterns, like the way chlorophyll reflects light in specific wavelengths. Even the texture of a planet's surface, whether it's smooth or rugged, might hint at geological processes influenced by life, but again, nature loves to throw curveballs. Volcanic activity, for instance, can create features that look eerily similar to those produced by living systems. Detecting these biosignatures isn't as simple as pointing a telescope and snapping a photo. It requires cutting-edge technology and a deep understanding of planetary science. Instruments like spectrometers break down the light from distant stars, revealing the chemical fingerprints of the planets orbiting them. Space telescopes, like the James Webb, are designed to peer into the atmospheres of exoplanets, searching for those elusive traces of life. Yet, even with these tools, the search is fraught with uncertainty. A single measurement might not be enough to confirm life. It often takes a mosaic of evidence to paint a convincing picture. The hunt for biosignatures is a delicate dance between hope and skepticism. Every discovery brings us closer to answering humanity's oldest question, but it also reminds us of the complexity of the universe. As we continue to explore, we're not just searching for life, we're learning to read the language of the cosmos, one clue at a time. As we peer into the vast expanse of the cosmos, the tools we use to search for life have become more powerful than ever. Gone are the days when our understanding of distant worlds was limited to blurry images and vague guesses. Today, cutting-edge technology is transforming the way we explore the universe, bringing us closer than ever to answering one of humanity's most profound questions: are we alone? At the forefront of this revolution are space telescopes like the James Webb Space Telescope and ground-based observatories equipped with advanced instruments. These marvels of engineering allow us to study planets orbiting stars beyond our solar system with incredible precision. By analyzing the light that passes through or reflects off these distant worlds, scientists can uncover clues about their atmospheres, surfaces, and even potential signs of life. One of the most powerful tools in this quest is spectroscopy. Imagine a cosmic fingerprint, a unique pattern of light that reveals the chemical makeup of a planet's atmosphere. Spectroscopy allows us to decode these fingerprints, identifying molecules like oxygen, methane, or water vapor that could hint at biological activity. It's like reading a planet's story through the light it emits, and it's giving us unprecedented insights into the conditions on worlds light years away. But spectroscopy is just one piece of the puzzle. Advanced imaging techniques are also playing a crucial role. By capturing high-resolution images of exoplanets, we can study their surfaces, weather patterns, and even the potential presence of oceans or vegetation. Ground-based observatories, equipped with adaptive optics, are now able to cancel out the blurring effects of Earth's atmosphere, delivering crystal-clear views of distant stars and their orbiting planets. And then there are the indirect methods, like the transit technique, which detects tiny dips in a star's brightness as a planet passes in front of it. This not only helps us locate exoplanets, but also provides data on their size, orbit, and even density. Combined with other tools, these methods are painting a vivid picture of the diversity of worlds beyond our solar system, from scorching gas giants to rocky, Earth-like planets in the habitable zone. The search for life is no longer confined to science fiction. With each technological leap, we're inching closer to discovering whether life exists elsewhere in the universe. And as these tools continue to evolve, so too does our ability to explore the cosmos, not just as observers, but as explorers on the brink of a discovery that could change everything we know about our place in the universe. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Given the sheer scale of it all, it seems almost inevitable that life should exist somewhere beyond Earth. Yet here we are, gazing into the cosmos, and so far, the answer to the question, "Where is everyone?" remains elusive. This is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously posed the question during a casual conversation in the 1950s. If the conditions for life are so common, why haven't we found any signs of it? One possibility is that life itself is incredibly rare. Even if the universe is teeming with planets in the so-called Goldilocks Zone, where conditions are just right for liquid water and potentially life. The leap from simple chemistry to complex organisms might be far more difficult than we assume. Earth's own history shows that life took billions of years to evolve from single-celled organisms to the diversity we see today. Maybe the odds of that happening elsewhere are astronomically low. Another explanation lies in the challenges of interstellar communication. The distances between stars are so vast that even light, the fastest thing in the universe, takes years to travel from one star system to another. Imagine trying to have a conversation with someone on the other side of the planet, but instead of seconds, your messages take decades or even centuries to arrive. Civilizations might simply be too far apart to ever make meaningful contact, or perhaps they've developed technologies we can't even comprehend, making their signals invisible to our current methods of detection. Then there's the darker side of the paradox, the possibility that intelligent civilizations might not survive long enough to make their presence known. Advanced societies could face existential threats, climate collapse, nuclear war, or technological disasters that wipe them out before they can establish contact with others. If this is the case, the silence we hear might be a sobering reminder of the fragility of intelligence in the cosmos, but there's also a more optimistic angle. Maybe we're just looking in the wrong way, or at the wrong time. The universe is nearly 14 billion years old, and humanity has only been scanning the skies for a tiny fraction of that. What if we're like a child shouting into a canyon, unaware that an echo might return long after we've stopped listening? The search for extraterrestrial life is still in its infancy, and every new discovery brings us closer to understanding whether we're truly alone or just waiting for the right moment to connect. What if the universe isn't as empty as it seems? What if, scattered across the vast expanse of the Milky Way, there are other civilizations reaching out into the cosmos, just like us? This is the tantalizing question at the heart of the Drake equation, a formula designed to estimate the number of intelligent civilizations in our galaxy. Developed by astronomer Frank Drake in 1961, this equation isn't about giving us a definitive answer, it's about framing the conversation. It's a way to think critically about the factors that might influence the existence of other life forms out there. So, what exactly is the Drake equation? At its core, it's a series of variables multiplied together, each representing a key factor in the likelihood of detecting intelligent life. The equation starts with the rate at which stars form in our galaxy, then narrows things down step by step. How many of those stars have planets? How many of those planets could support life? And of those, how many might actually develop intelligent civilizations capable of communicating across the stars? Each variable is a piece of the puzzle, and together they give us a framework to explore the possibilities. But here's the catch: many of these variables are still shrouded in uncertainty. For example, we now know that planets are incredibly common, thanks to discoveries made by telescopes like Kepler and James Webb. But what about the next step? How many of those planets are in the so-called Goldilocks Zone, where conditions are just right for liquid water and potentially life to exist? And even if life does emerge, how likely is it to evolve into something intelligent and technologically advanced? These are the kinds of questions that keep scientists debating and refining the equation. One of the most fascinating aspects of the Drake equation is how it reflects our own evolving understanding of the universe. When Drake first proposed it, we didn't even know if planets existed outside our solar system. Now, we've confirmed thousands of exoplanets, and the number keeps growing. But with every discovery, new questions arise. Are we alone in the universe, or is it teeming with life? The Drake equation doesn't give us a final answer, but it invites us to keep searching, to keep wondering, and to keep exploring the infinite possibilities that lie beyond our own corner of the cosmos. Time is one of the most fascinating and humbling factors in the search for life beyond our planet. The universe is nearly 14 billion years old, and in that vast expanse of time, stars have ignited, planets have formed, and entire galaxies have risen and fallen. Life, as we know it, might have emerged and vanished countless times across the cosmos, hidden in the distant past or waiting to appear in the far future. This raises a profound question. Are we searching for life in the right moment, or are we just a fleeting glimpse in the grand timeline of the universe? Consider this: stars, the engines of creation, have life cycles of their own. Some burn bright and fast, lasting only a few million years before exploding in spectacular supernova. Others, like our Sun, shine steadily for billions of years, providing the stable conditions necessary for life to thrive. But even these long-lived stars eventually fade, and their planets may no longer harbor life. This means that the window for life to emerge on a planet is not infinite, it's tied to the lifespan of its star. If life arose on a world orbiting a short-lived star, its time to flourish could have been tragically brief, leaving behind only faint traces for us to discover. And then there's the lifespan of civilizations themselves. Human history spans just a few thousand years, a blink of an eye, compared to the age of the universe. If intelligent life exists elsewhere, how long do civilizations typically last? Do they endure for millennia, or do they rise and fall in mere centuries? The challenge is that even if life once thrived on a distant planet, the evidence of its existence might have eroded over billions of years. Ancient cities, if they ever existed, could have crumbled into dust, and atmospheres once rich with oxygen might have transformed beyond recognition. The search for life, then, isn't just a matter of space, it's a race against time, but time also offers hope. The universe has billions of years ahead of it, and countless stars and planets are yet to form. Life could arise again and again in places we've yet to imagine. Perhaps we're not just searching for life that once was, we're also looking for life that could be, waiting in the cosmic wings for its moment to shine. The role of time in this search reminds us that the universe is both a graveyard and a cradle, holding secrets of the past and the promise of the future. And as we peer into the depths of space, we're also peering into the depths of time itself, searching for answers that may lie just beyond our reach. When we think about the origins of life, it's easy to picture a carefully orchestrated process, as if the universe had a grand plan. But what if it wasn't so deliberate? What if life began not by design, but by chance? The idea that randomness played a pivotal role in the emergence of life is both fascinating and humbling. Imagine the early universe, a chaotic dance of particles and energy, where countless chemical reactions unfolded without direction. Among those reactions, a few just happened to create the building blocks of life: organic molecules like amino acids and nucleotides. These molecules didn't form with purpose. They were the result of random collisions and energy transfers in the primordial soup of Earth's ancient oceans. This randomness didn't stop there. Over millions of years, these simple molecules combined in countless ways, most of which led nowhere. But every so often, by sheer chance, something remarkable occurred: a molecule that could replicate itself, or a structure that could harness energy. These rare, accidental breakthroughs became the foundation for life as we know it. It's like rolling a cosmic dice trillions of times until, against all odds, the perfect combination comes up. But what does this mean for the possibility of life elsewhere in the universe? If life on Earth arose from a series of fortunate accidents, does that make us unique, or is the universe teeming with similar chance events? The answer lies in the sheer scale of the cosmos. With billions of galaxies, each containing billions of stars and planets, the odds of these conditions repeating somewhere else seem far less remote. Even if the emergence of life is a rare event, the universe has both the time and the space to make it happen again and again. This perspective shifts the question from "Are we alone?" to "Where else might life have taken hold?" The role of chance in the origins of life reminds us that science isn't just about certainty, it's about probabilities and possibilities. It's a story of trial and error, of chaos and opportunity, and ultimately, of the incredible resilience of nature. Whether life is a cosmic fluke or a universal inevitability, the journey from stardust to living organisms is a testament to the unpredictable beauty of existence. When we look up at the night sky, it's easy to marvel at the vastness of the cosmos and wonder if we're truly alone. Intelligence, whether human or extraterrestrial, has the potential to be one of the most transformative forces in the universe. It's not just about the ability to think, but the capacity to create, innovate, and leave a lasting mark on the fabric of existence. From the earliest tools carved by human hands to the satellites orbiting distant planets, intelligence drives progress and shapes the cosmos in ways that are both subtle and profound. One of the most fascinating aspects of intelligence is its ability to transcend its origins. Take, for example, the Voyager probes launched by NASA in the late 1970s. These spacecraft carry golden records etched with sounds and images from Earth, a testament to human ingenuity and our desire to reach out to the stars. They're not just pieces of technology, they're messages in a bottle, floating through the cosmic ocean, waiting to be discovered by someone or something out there. this raises an intriguing question. If intelligence exists elsewhere, what might its creations look like? Detecting signs of intelligent life, however, is no simple task. The universe is unimaginably vast, and the distances between stars are so immense that even light takes years, centuries, or millennia to traverse them. Add to that the challenge of recognizing forms of intelligence that might be entirely different from our own, and the search becomes even more daunting. Are we looking for signals, structures, or something else entirely? The search for extraterrestrial intelligence, or SETI, has been scanning the skies for decades, but so far, the cosmos remains silent. Yet this silence doesn't mean we're alone. It might just mean we're not looking in the right way, or that intelligent life is rarer than we'd hoped. The implications of finding, or not finding intelligent life are profound. If we discover that we're not alone, it could redefine our understanding of life's place in the universe. What would it mean to share the cosmos with another civilization? Would it inspire cooperation or competition? On the other hand, if we confirm that intelligence is vanishingly rare, it might underscore the preciousness of our own existence. Either way, the search itself reminds us of the boundless curiosity that drives humanity to explore, to question, and to dream. Ultimately, intelligence is more than just a trait, it's a catalyst. It transforms starlight into energy, raw materials into tools, and ideas into realities. And as we continue to peer into the depths of space, we're not just searching for others, we're also learning more about ourselves and the extraordinary potential we hold within us. What if consciousness isn't just a byproduct of the brain, but something far more fundamental to the fabric of the universe itself? This is the question that has puzzled philosophers, scientists, and thinkers for centuries. Consciousness, the ability to perceive, to feel, to think, is one of the most profound mysteries we've ever encountered. It's the invisible thread that connects us to the cosmos, yet its true nature remains elusive. At its core, consciousness is what allows us to experience the world. Without it, the universe would exist, but there would be no one to observe it, no one to marvel at its beauty or question its origins. But where does consciousness come from? Some theories suggest it's an emergent property of complex systems, like the human brain. Others propose it's a fundamental aspect of reality, woven into the very fabric of space and time. Imagine the universe as a vast, interconnected web, with consciousness as one of its essential threads. It's a perspective that challenges us to rethink not just who we are, but what the cosmos itself might be. The scientific study of consciousness is still in its infancy, but breakthroughs are beginning to shed light on this enigma. Neuroscientists are mapping the brain's intricate networks, searching for the neural signatures of awareness. Meanwhile, quantum physicists are exploring the possibility that consciousness might play a role in the behavior of particles at the subatomic level. Could it be that consciousness isn't just observing the universe, but actively shaping it? The implications are staggering, opening doors to questions about the nature of reality itself. And what about consciousness beyond Earth? If it's a fundamental aspect of the universe, could it exist elsewhere, on distant planets in other galaxies, or even in forms we can't yet imagine? The search for extraterrestrial intelligence often focuses on finding signs of life, but perhaps we should also be looking for signs of consciousness. After all, the universe is vast, and its mysteries are far from fully understood. As we continue to explore these questions, we're reminded of how much we still have to learn. Consciousness isn't just a scientific puzzle, it's a window into the deeper truths of existence, and as we peer through that window, we might just find that the universe is far more alive, far more interconnected than we ever dared to imagine. In the grand tapestry of the universe, humanity occupies a unique and humbling position. We are quite literally made of stardust, our very atoms forged in the hearts of ancient stars that lived and died billions of years ago. This connection to the cosmos isn't just poetic, it's a reminder that we are an integral part of a much larger story. But what does it mean to be a small yet significant thread in this cosmic narrative? Let's explore our origins, our potential, and the responsibilities that come with being Earth's stewards. Our journey begins with the elements that make up everything around us and within us. The carbon in our DNA, the iron in our blood, and the oxygen we breathe were all created in the fiery cores of stars. When those stars reached the end of their lives, they exploded, scattering these elements across the universe. Over eons, these building blocks came together to form planets, oceans, and ultimately, life. In this way, we are not just observers of the cosmos, we are its direct descendants. This profound connection underscores our place in the universe not as outsiders, but as active participants in its ongoing evolution. Yet, as much as we are products of the cosmos, we also hold the potential to shape its future. Humanity's curiosity and ingenuity have already taken us beyond our planet, allowing us to glimpse distant worlds and uncover the secrets of the universe. From the first steps on the moon to the breathtaking images sent back by telescopes like Hubble and James Webb, we've proven that our reach extends far beyond Earth. But with this potential comes a profound responsibility. As we look to the stars, we must also look inward, recognizing the delicate balance that sustains life on our own planet. The challenges we face are immense. Climate change, resource depletion, and environmental degradation threaten the very systems that allow us to thrive. Yet, these challenges also present opportunities to innovate, to collaborate, and to reimagine our relationship with the world around us. By addressing these issues, we not only secure our future on Earth, but also lay the groundwork for becoming a spacefaring civilization. Imagine a future where humanity thrives not just on one planet, but across many. It's a vision that begins with the choices we make today. This dual role, as both explorers and stewards, defines our place in the cosmic story. We are tasked with protecting the fragile oasis we call home while reaching out to the vast unknown. It's a balancing act that requires wisdom, humility, and an unwavering commitment to the greater good. The universe has given us the tools to shape our destiny, but it's up to us to use them wisely. As we stand at the crossroads of history, we have the chance to leave a legacy that echoes across the stars, a testament to what humanity can achieve when we embrace our role in the cosmic story. The cosmos has always been a source of wonder, but the future of space exploration is poised to take that wonder to unprecedented heights. Imagine a world where humans set foot on Mars, where robotic explorers uncover secrets on the icy moons of Jupiter and Saturn, and where telescopes peer deeper into the universe than ever before. These aren't just dreams, they're missions already in motion. One of the most ambitious goals on the horizon is sending humans to Mars. Agencies like NASA and private companies such as SpaceX are working tirelessly to make this a reality. But getting there isn't just about building a rocket. It's about solving challenges like radiation exposure, maintaining life support systems, and ensuring astronauts can survive the harsh Martian environment. And once we're there, the real work begins: studying the planet's geology, searching for signs of ancient water, and perhaps even preparing for future colonization. But Mars is just the beginning. Some of the most exciting prospects lie in the outer reaches of our solar system. Moons like Europa and Enceladus, with their hidden oceans beneath icy crusts, could hold the key to finding extraterrestrial life. Missions like Europa Clipper aim to study these moons up close, analyzing their plumes of water vapor for signs of microbial life. The idea that we might find life, even in its simplest form, somewhere other than Earth is both thrilling and humbling. Of course, none of this would be possible without incredible advancements in technology. From next-generation propulsion systems to AI-driven rovers, innovation is the backbone of space exploration. One example is the James Webb Space Telescope, which has already revolutionized our understanding of the universe by capturing images of distant galaxies and analyzing the atmospheres of exoplanets. These tools aren't just expanding our knowledge, they're reshaping how we think about our place in the cosmos. Yet, with every leap forward, challenges remain. Space is vast, unpredictable, and unforgiving. The distances involved are staggering, and the environments we explore are often hostile to life as we know it. But it's precisely these challenges that drive us to innovate, to push boundaries, and to dream bigger. Every mission, every discovery, brings us closer to answering some of humanity's oldest questions. Are we alone? How did the universe begin, and what's our role in this grand cosmic story? As we look to the future, one thing is certain: space exploration is about more than just science. It's about curiosity, collaboration, and the unshakable belief that there's always more to discover. Whether it's a rover drilling into Martian soil or a spacecraft skimming the surface of a distant moon, each step forward is a testament to human ingenuity and our endless desire to explore the unknown. Space exploration is not a solo mission, it's a symphony of collaboration. Across the globe, nations and organizations are pooling their resources, knowledge, and ambitions to push the boundaries of what we know about the universe. This isn't just about sending rockets into the sky, it's about uniting humanity under a shared goal of discovery. Take the International Space Station, for example. This orbiting laboratory is a testament to what we can achieve when countries like the United States, Russia, Japan, and members of the European Space Agency work together. It's a hub of scientific research, where astronauts from different nations live and work side by side, conducting experiments that benefit us all. But collaboration doesn't stop at governments. Private companies are now playing a pivotal role in shaping the future of space exploration. SpaceX, Blue Origin, and others are not just competing with traditional space agencies, they're partnering with them. These companies bring innovation, speed, and fresh perspectives to the table, helping to lower costs and accelerate progress. For instance, SpaceX's reusable rockets have revolutionized how we think about launching payloads into orbit, making space more accessible than ever before. What makes this partnership between public and private entities so powerful is the blending of expertise. Government agencies like NASA and the European Space Agency bring decades of experience and institutional knowledge, while private companies inject cutting-edge technology and entrepreneurial spirit. Together, they're tackling challenges that no single entity could solve alone, from developing sustainable life support systems for long-duration missions to designing spacecraft capable of reaching distant worlds. This spirit of cooperation extends beyond borders. Space exploration has always been a unifying force, reminding us that the challenges we face and the opportunities we seek are bigger than any one nation. Whether it's sharing data from telescopes, collaborating on robotic missions to Mars, or planning future crewed missions to the Moon and beyond, the global space community is proving that when we work together, the sky isn't the limit, it's just the beginning. As humanity reaches further into the cosmos, the excitement of discovery comes with a profound responsibility. Space exploration isn't just about what we can do, it's about what we should do. One of the most pressing ethical questions is the risk of contamination. When we send probes, landers, or even humans to other worlds, we risk introducing Earth's microorganisms to environments that might harbor their own unique forms of life. Could we unintentionally wipe out an entire ecosystem before we've even discovered it? This isn't science fiction. It's a real concern that scientists and ethicists are grappling with today. Then there's the question of extraterrestrial life itself. If we were to discover life, whether microbial or intelligent, what rights would it have? Would we treat it as a resource to study, or as a form of life deserving of respect and protection? History has shown us the dangers of exploitation, from colonialism to environmental destruction. Space offers us a chance to do better, to set a new standard for how we interact with the unknown. But that requires us to think carefully about our actions and the values we carry with us beyond Earth. Responsible exploration also means considering the long-term impact of our presence. Mining asteroids, colonizing planets, and even altering celestial environments, these activities could reshape the solar system in ways we can't yet predict. Who gets to decide how these resources are used, and who ensures that the benefits are shared equitably rather than exploited by a few? These aren't just technical challenges, they're moral ones, requiring us to balance ambition with accountability. Ethical guidelines for space exploration are no longer optional, they're essential. Organizations like NASA and the United Nations are already working on frameworks to address these issues, but the conversation needs to go further. It needs to include scientists, policymakers, ethicists, and the public. After all, space doesn't belong to any one nation or corporation. It belongs to all of us. As we take these next steps, we're not just exploring new worlds, we're defining who we are as a species and what kind of legacy we want to leave behind. Space exploration is more than just rockets and distant galaxies. It's a gateway to curiosity, discovery, and the kind of wonder that can spark a lifelong passion for learning. Education plays a vital role in nurturing that spark, especially when it comes to inspiring the next generation of scientists, engineers, and dreamers. Think about it, every mission to Mars, every image from the James Webb Space Telescope, every breakthrough in astrophysics has the potential to ignite a young mind's imagination. But how do we channel that inspiration into something tangible? That's where STEM education comes in. By integrating science, technology, engineering, and math into classrooms, we give students the tools to not only understand the universe, but to contribute to its exploration. Public outreach is another key piece of the puzzle. Events like stargazing nights, planetarium visits, and hands-on workshops bring the cosmos closer to home, making space science accessible to everyone, not just those in academic settings. And let's not underestimate the power of media in shaping how we see the universe. Documentaries, YouTube channels, and even sci-fi movies can simplify complex ideas and make them relatable, showing us that the mysteries of the cosmos are within our reach. When you combine these elements, education, outreach, and media, you create a powerful ecosystem that doesn't just teach facts, but fosters a deep, enduring love for exploration. But it's not just about creating future scientists. It's about cultivating a society that values curiosity, critical thinking, and the relentless pursuit of knowledge. After all, the challenges of tomorrow, Whether it's climate change, energy sustainability, or even interstellar travel, will require creative minds and collaborative efforts. By investing in education today, we're not just preparing individuals for careers, we're shaping a future where humanity continues to push the boundaries of what's possible. And isn't that what space exploration is all about? As we reach the end of our cosmic exploration, it's impossible not to feel a deep sense of awe at the story we've uncovered. The universe, in its vastness and intricacy, has revealed itself as a masterful alchemist, turning starlight into the very essence of life itself. From the fiery hearts of stars to the delicate chemistry of planets, every step in this process reminds us of how interconnected we are with the cosmos. Each atom in our bodies, every breath we take, carries the legacy of stars that burned billions of years ago. This isn't just science, it's poetry written in the language of the universe. And as we stand here, looking up at the night sky, we're reminded that we're not just observers of this grand cosmic dance, we're participants, woven into the fabric of existence itself. The journey doesn't end here, though. There are still countless mysteries waiting to be unraveled, questions begging to be answered. So let's keep our curiosity alive, our sense of wonder intact, and our eyes fixed on the stars. Thank you for sharing this journey with us. If you've enjoyed this cosmic adventure, be sure to hit that subscribe button and join us as we continue to explore the wonders of the universe together. Until next time, keep looking up, the cosmos is calling.